Okay, welcome back to part two here. So here we go, number three. I'm calling it part A. I know it probably doesn't say A on your paper, but here we go. We want the derivative of this integral. Now, the hard part again for people is gonna be just notation, because you're not used to seeing this. It's one of those things that it all kind of runs together. You know, you think, oh wait, am I finding area under the curve? What am I doing? Do I do the antiderivative? And so it's going to be a tough task of keeping these straight. But when you see derivative and it's already an integral, that's something different that triggers in your brain, and you need to think, oh, those undo each other. I just rewrite the original function as long as the conditions are right. So let's look at that. What's wrong with 3a? These are not the correct way. I don't have a bottom bound of a real number, and my variable is actually on the bottom, not the top. So I need to switch those. Here come the properties we talked about, because when you make a switch of a and b and rewrite it, so I'm going to go ahead and put 5 on the bottom where it's supposed to go and x on top. But what do you have to do? You change the sign. So now it's negative from 5 to x of 3t sine of t dt. And now it's as easy as those first couple problems I gave you. You simply write the negative, of course, don't leave that out now, and you plug this in. So that's going to be negative 3x sine of x. The derivative and the integral canceled each other out. Now, here's these last two are really hard, and I don't know if I left myself enough space. So if you don't mind, I'm actually going to erase 3a now so that I have room for 3b, so I can kind of start over to the left a little bit more. Okay, so on 3b, the big dilemma is I don't have a real number for my bottom bound or my top bound. So I can't even switch it like I did in that last problem. This is a 2x, that's an x squared. Very tricky problem. Once you see it, you're gonna go, oh, okay, that makes sense, that's not bad. But it's a tough problem just to kind of think outside of the box. So instead of having you partner up and toil with a partner for 15 minutes like I would have in class on these last two, I'm gonna just tell you, lucky you, lucky you. Here we go. I'm going to use that property called additivity for definite integrals. So I'm going to draw myself, or draw you, a picture of a random function. Pretend that's 1 over 2 plus e to the t. And I'm going to put on here 0. I'm going to put on here 2x. And I'm going to put on here x squared. Okay? Now, if I had to re-represent this so that I had a bottom bound that was a real number, and by the way, I could have called this 1 or 0 or whatever you want. I just call it 0 to make it easy. So I did make that value up. There's nothing special about that being a 0. Again, I could have really picked anything. Actually, let me kind of backtrack here as I'm thinking out loud on the fly. I do need to be careful, because if you pick something that's less than 2, you'll have issues, because then this would actually be bigger than that. We don't want that. So actually I picked something a little bit trickier than I thought I would. So let's pick 4. You need any number as long as this value is smaller than the x squared. All right, so we got that. I made that up. Here we go. I'm going to write this as 2 using additivity. I'm going to write this as the integral of the whole thing from 4 to x squared of 1 over 2 plus e to the t dt minus the integral of just this section. Sorry, I said that wrong. Let me start over. I want the integral of the whole thing from 4 to x squared, that's this one, minus just this section, so 4 to 2x. Now think about it. If you took the whole thing minus just this part here, what would that leave you with? That would leave you with the part that we're actually interested in. So from 4 to x squared minus 4 to 2x, and that should get us our value. And now we were able to abide by the rules of writing definite integrals as functions. We have our letter on the bottom, variable on top. Now to add to the matter, there's still some chain rule involved because both of them have something other than a 1x. So let's keep going here. Plugging the input in right here would be 1 over 2 plus e, and it's e to the t, so now it's e to the x squared. You plug that exact thing in, but don't forget chain rule, times 2x. Over here, this is going to be 1 over, you plug the 2x in, so 2 plus e to the 2x. Again, don't forget chain rule, times 2. Putting those all together, we end up with 2x over 2 plus e to the x squared minus 2 over 2 plus e to the 2x. And now we have our answer, our derivative of that definite integral. Had to use the chain rule, had to use additivity to break it apart into two pieces, but there's our answer. Last question is different than all the other questions. And again, this would have been one where I would have had you partner up and really think this through. And once you see it, again, it's not bad, but before you do, it's tricky. So find a function, f of x, that has a derivative of tan of x, and it has to satisfy this condition. Now immediately, what people think, let me just give myself a little more space here. Immediately what people gravitate to in this problem is they think, oh, okay, it has to have a derivative of tan of x. Oh, okay, I need the antiderivative of tan of x. Not bad logic, all right? And then people start thinking, okay, what's the antiderivative that when I take the derivative, I get tan of x? And people think and think, wait, is it secant squared? Nope, that's the other way. There is no known antiderivative for tan of x, at least that I know right now. Now, maybe in a very complex algorithm, one could be determined, or maybe it's just something that's beyond what we're worrying about in this class. But for now, let me just tell you, there is not an easy antiderivative for tan of x. There is for a lot of our other functions, not for tan of x. So what do? You cheat. You use the fundamental theorem, part 1, to kind of bend the rules a little bit. Think about this. What's our theme today? The derivative and an integral, they cancel each other out and leave you with the original function. So let me word it this way. If my goal is to be left with, or let me start over. If my goal is when I take a derivative that I'm left with tan of x, then I need to write an integral of tan of t, just like I've been doing, all right? Think about that. If I write an integral of tan of t, when I take the derivative, I should get the original function tan of x. So let me lay that groundwork down first, okay? I know there's some other details that we need to get first, but think about just loosely before we fill in the other details. When I take the derivative of tan of t dt, shouldn't the derivative come out as tan of x now? So we got that part. What about this 3 and 5? So here's what we're gonna do. We're gonna make our bottom bound 3, which is the input, that's on purpose, and our top bound, of course, is gonna be x. That's how we write definite integrals. I'm not done yet, but think about it right now. If you were to plug in an input right now of 3, right here, and actually go through the process of really finding the area under the curve, what would 3 plugged in here actually give you for a value there? Well, 3 on bottom, 3 on top, it would give you 0, right? Okay? Well, we don't want f of 3 to give you 0. We want f of 3 to give you 5. So there's a really easy fix to that. Add 5. So it's kind of a neat little trick. If you make the bottom bound that number so that when you actually plug the 3 in up there on top, you get a 0, then it's real easy to get the desired 5 by simply adding an extra 5 on, okay? So you're gonna see a couple of these pop up here and there, as well as some of these other variety. I think it's a lot easier to get 5 or 6 or 7 of you to kind of understand this than it is 70 or 80 of you with all the seniors here. So it's kind of a blessing in disguise that this is coming now, I think, because this would have been a tough one for everybody. But I think you guys can handle this. And as always, let me know if you have any questions. Tomorrow will be a practice day where you'll do more of this so that you're ready for your quiz Thursday. For homework tonight, I wrote it down here. It's also probably written on today's assignment. Your homework is going to be page 302. And I want you to do numbers 3 to 24, but only do the multiples of 3. So you don't have, you only have like 8 questions as opposed to 24 questions. Write them down, scan that when you're done, show all your work, and then submit as a PDF using your scanning tool. Hope that made sense, guys. Have a good one. I'll talk to you later.